Thank you very much, Franco, and thank you for organizing such an interesting session. What I really want to talk about, and these are just so you know, the flyover slides, these will appear when ACI puts them up there so everybody remembers what the session was about and what the learning objectives are. But what I'd really like to talk about is really what is the big push that's happening right now in the industry, and what is it that we're trying to do when we talk about accelerating these reactions. So to start with, what we're really talking about here is part of this big push is using the data that NRMCA generated through their Athena program is really to establish what's going on right now in terms of the total GWP of mixtures throughout the US versus the compressive strength. So if you take, for example, that document and you plot the data that's in the tables, what you will notice is that there's a trend that the global warming potential increases as a function of compressive strength. Now, what ACI 323 is encouraging us all to do is to move from this line down to the red line by some value alpha, right? So the idea here is we're really trying to reduce the global warming potential, and I think the most important thing for us to start out and understand is, at best, compressive strength is very much an incomplete measure of what it is that we're trying to do, right? There are different levers that we can pull on other than just changing compressive strength to get there, and a big part of this is what we're going to be talking about. So right now, industry is really working hard to reduce the global warming potential, right? But there's questions on how we should do this and really where producers need to start with this, because they're being asked to do this today. They're being asked to do this on real projects right now, all right? And there's lots of very interesting things that are coming in the future, but one of the questions is how do we make immediate change now? So the first thing that I want to do is I want to point out a very typical mixture, and some of you will look at this and say, well, that's an Indiana mixture, that doesn't look like a lot of other DOT mixtures. A lot of the DOT mixtures look very similar because in the 1960s they all started with the same recipe. Right? There were recipe specifications, they were promoted across the country when the interstate system was built, so lots of the original mixture designs all look very similar. If we take a typical mix that uses only cement, and I've had some people say, well, that doesn't happen in our DOT because we use other types of materials. There are some SCMs used, not nearly in the volume that they need to be used. There is a substantial amount of plain concrete that is still produced and placed. And if you look at this concrete and you sum up where the global warming potential is coming from, you immediately get the conclusion that 85 to 95% of the carbon is coming from the cement. So this is why there's such a big push to reduce the cement content, reduce the clinker content, right? So what we've been doing for the last 15 or so years is we've been saying there's really three big pushes that we need to make when we talk about long-term sustainability. The first is we need to reduce the cement content in our mixtures, and many agencies have started to do this. They've started to reduce minimum cement contents. They've started to optimize aggregations. They've started to really encourage pushing that value down. Now that is awesome, and there's been huge progress made with agencies taking 50 or 100 pounds of cement out of their mixture and getting very equivalent performance. I do want to point this out, though, because that was something that helped them with risk before, right? So they had some buffer zone in their mixtures. So they've reduced some of that buffer zone to start with. Now we're saying, in addition to reducing that buffer zone, please also reduce the amount of clinker, right? So you see the 3 cows that run around, right? And they tell you to eat more chicken, right? We want to reduce the amount of clinker that's in the system. And this is kind of a new concept that you hear people talking about, but it's really not the cement that's the problem, it's the clinker that's the problem. It's the clinker that has the high GWP in it, right? And the third thing, and I think, or the third part of this, and I think this is the most important piece of this, concrete for a long time has been known as the long-lasting material, right? If we start putting out materials with a low global warming potential on the A1 to A3 LCA analysis, and we don't provide long-term durability, this is going to be a big problem for the industry. There have already been materials that have been demonstrated that they're getting 3 or 4 years before they're having to be replaced. And that's not good when the agency is requiring or expecting a 50 to 75-year life. Right? So we have to think about the life cycle performance part of this, and we have to go past A1 to A3 to get to an A1 to D LCA, or we have to come up with a way to think about the carbon over its life. Now, this led to some changes, and these changes go back 20 years. It's been 2 decades since some of these changes started to take place. Some of you may have noticed that 20 years ago, ASTM C150 changed slightly, and when ASTM C150 changed slightly, your clinker, which are these white dots, the black stuff in the background would represent your water in your system, you'll notice that there's some yellow dots that start showing up in your C150 cement. Those yellow dots are limestone or calcium carbonate that was being discussed earlier. And almost no one got excited when this was added into the system because, as Franco mentioned earlier, adding a little bit creates the carboaluminate phases that reduce porosity and increase strength. So when strength went up a little bit, gave people a little bit more of a cushion, nobody was super worried about it. It stayed around 3 to 5%. Right? At the same time, there were other groups around 2009 that started looking at 595 and started looking at the 1L and the 1T cements. And one of the things that they started to look at when they started bringing these blended cement systems in is there was a synergistic effect when you increase the calcium carbonate when you put stuff like slag interground into the mixture. And part of the reason that there's that synergistic effect is what we were talking about earlier in Franco's talk, where all of a sudden we've got extra alumina in the system, we have more carboaluminate reaction, so we're getting that to move over to a higher limestone concentration. Right? So there are lots of these materials that have been pushed out, and they've been pushed out at scale. And these are 30% global warming potential reductions, even as far as 15 years ago. All right? You're seeing the same thing now happening with natural pozzolans, calcined clays, right? And I think it's better for us to just remember, we can put in anything we want. We can call it IBM, we can call it X, we can call it Y. It's sources of silica and alumina that are the primary drivers. The alumina gives you more of that monocarbonate, hemicarbonate reaction to take place in these systems, right? Now, I think it's also important to remember that while there's lots of exciting new things that are on the horizon in terms of cement production, right? The pocket sun that was coming up earlier that was being talked about, where we can heat cement differently, or people who are making cement with different approaches. To a large extent, the vast majority of concrete that's being placed today is being placed with our existing knowledge. And our existing knowledge is clinker-based, right? If you don't believe this, look at the vast amount of concrete knowledge that's out there at ACI. It makes the assumption that cement and concrete are clinker-based, right? Our industrial complex, when you look across this map, right, there are plants, the little dots are plants that are good at making clinker, all right? It's all based on clinker cement. So as we start to use less clinker, we have less of the thing that was reacting that our codes, our standards, our specifications, our base of knowledge was based on, and we have to redevelop some of our understanding. In general, the alternative or the supplemental cements, ASCM, SCM, they are reacting more slowly, and many times they're counting on something else in the system to have reacted first for them to be able to react. So before the silica can react, the calcium hydroxide has to precipitate out. So it's not reacting from time zero, all right, necessarily. It's reacting after the calcium hydroxide precipitates out of the mixture, right when you start to go into stiffening and early strength development. It's a slower reaction. And this has changes not only in the long-term strength, which is what lots of us focus on, but it has lots of changes in how we place and cure our concrete, and in particular, how the early strength develops around those mixtures. So this impacts things like bleeding and early strength development. So now I want to start to talk a little bit about some of the concepts that we'll hear people discussing and then get into some more details. But why are we after, why is the strength gain more slow? all right? Because the clinker is not, it's not that the clinker is reacting more slowly, it's we have less clinker in the system, right? The clinker rate of reaction isn't really changing, we have less of it. So the image to the right, we've got this one up here where we've got sort of the bluish stuff, that's the pore solution in the system. The circular things are the cement particles. I know cement particles aren't circular. I'm a really bad artist, I apologize. All right, these things that look like a dreamsicle up here, the orange and white stripe, right, those are our SCMs that are in our mixture. So if we do a volume replacement, which we are not currently doing as an industry, but should, because most of these materials have a different density than cement, if we do a volume replacement, we have the same initial porosity, right? The material is going to flow in a very similar way, right? The other thing, though, is if these things start reacting, you can think about how these materials react and how they stiffen as sort of these cement particles growing some kind of a Velcro on their surfaces. And when that Velcro starts to interact with each other, that's all of a sudden when the rates of reaction start to slow down. When we replace a lot of that clinker with something else, we have more room for the Velcro to grow, right? So we actually get more reaction out of our clinker, and we're usually getting more effectively, and this is commonly referred to as the filler effect. So what I want to do now is I want to talk about three things that can be happening in these systems at the same time, and how we start to use these or design these to take advantage of these. So the first one is the filler effect, which I just mentioned. We will also talk about the nucleation effect, and then finally, our good old friend water to cement ratio we'll talk about, and how that can actually help us out immensely, and it will mean something different in these modern systems. So if we take a system with SCM in it, right, as I mentioned before, we're getting more of this hydration taking place. What we can actually do is use those heat curves. So this heat curve is exactly like the one we saw in the previous presentation. The only difference is we integrated that rate of heat to get the total heat that's being released as a function of time, right? So if we looked at the system that was the cement only, right, with a filler, right, and then we started to look at the system where we now start to get other things in it, we can start to quantify the effects of each one of these different types of components that's happening in the system. We get a certain amount of hydration that's happening due to the filler effect, which is the spacing of the particles. It's a relatively small amount of heat, right? But maybe it's 5% of the overall heat that's happening in the system, right? But it's, again, it's a little bit delayed because it's not impacting the original spacing of the particles. It's really when those particles start to impinge. The second one is nucleation, which I'll talk about in a second. And then we actually get the fly ash itself reacting, whether it's reacting to form CSH or whether it's reacting to form the monocarbonates. That's where we have, that's in the system. Now, the second effect is this idea of nucleation, right? And it's a pretty simple one. Reactions are lazy, right? They would rather start at an existing surface, right? It's a lot easier to lean up against the wall. We'll ask all the people in the back leaning up against the wall. It's easier to lean up against the wall than to stand straight up, right? Right? Just like a chemical reaction, it's easier to start the reaction off of a surface. So if you put in tiny nanoparticles, right, these can be limestone particles, calcium carbonate, these can be calcium hydroxide, these can be CSH. Those particles will actually start additional CSH growing that would have been growing in the through solution process, right? And again, that's maybe 5 or 10% of the overall reaction, all right? And we can promote this by actually adding some of these nanoparticles into the system. So some people may say, oh, nanotechnology, it sounds like it's space age. Well, people are doing it at commercial scale, right? They're adding these particles because they provide a nucleating agent that accelerates the overall reaction. The third thing, we can actually go way back in history, right? So we can go back 80 years and we can look at something that Powers did, right? And Powers said that the strength is related to this thing called the gel to space ratio, right? Now you can actually calculate out the gel to space ratio when you get to 1,000 KSI. All right, so if you said, I want to get to 1,000 KSI, what gel to space ratio do I need to be at? It is exactly 0.3087 according to Powers, right? You can actually figure out how much hydration had to happen in different water to cement ratio systems to get to that same gel to space ratio. right? And what you notice is, as you go to a lower water to cement ratio, it requires less degree of hydration. Now, I've used this because this has been the foundation of what we've understood about cements for the last 80 years, but we can do the exact same thing with thermodynamic modeling by adding in other components, by adding in the calcined clays, the slags, the fly ashes, and calculating that gel space ratio. And we do this all the time, right? So the basic thing that I want to start out with, and I'm going to do a first example here, one of the questions we get a lot is, can we use natural pozzolans at scale? Wrong question. This dam that was built in the 1950s used 28% pumice at scale. It's been done. They did it quite effectively. The dam is doing a great job. All right? This dam, 33% calcined clay at scale. All right? Done in the 1950s. All right? So the question isn't really, can we do it? The question is, how do we do it effectively, and how do we do it with some of these new tricks that we're learning? So here I'm going to show you some examples. The first example I want to show is where we're using a natural pozzolan. All right, we're going to put in some nano CSH seeds. It's a 0.4 water to cement ratio. It's a pumice natural pozzolan. I'm going to do a 25 and a 50% replacement of the clinker. I'm going to use a volumetric replacement because it has a different specific gravity than cement. If you just replace it by mass, you have more particles in there and you require more water to get workability. So when you do your water demand test, your water demand goes up because you've got less empty space in the system. If you do a volumetric replacement and account for the water absorption of the natural pozzolan, it's amazing. The water demand is much, much lower. I'm going to do everything based off of isothermal calorimetry, so we're going to try to match up the heat of hydrations. And as I mentioned, we did the natural pozzolan, we did it with an inert material, a quartz material that's inert, and then we're going to vary the nano CSH seeds. What we notice here is we see a reduction in heat, and you may say, that's great, what does that really mean? You have a reduction in reaction, right? A reduction in strength development in those two systems. Now, if we start looking at these longer term values, we'll go out to 7 days, for example, although we could take this out to longer term values, we could actually look at what's that heat of hydration in the system. So for our plain system, we might be up here around 260 joules per gram of cement. If I replace 25% of it, I drop down to this value right here, which is about 196, and if I replace 50% of it, half of this value is 130. Right? So this is the heat that I need to make up to get back to this value here. Right? How am I going to make that heat up? Well, part of that heat is going to simply come from the filler effect. Remember, by separating those particles out further, I can actually quantify the filler effect, and that's this point here, all right, to here. There's no nanoparticles in the system, this point to this point. I've added about 40 joules per gram back into the system just due to the filler effect, just due to using the clinker more efficiently. I still have more to make up, so I can add in the nano seeds, all right, using a very low dosage of those nano seeds, and I can make another 40 to 45 joules per gram of that material up. And what you'll notice is there's a general increase as you increase the dosage, but there's sort of a law of diminishing returns, right? When I first add the nano seeds in, I get some benefit, and then that benefit starts to go down as I go further and further along, right? So now I can actually start to design the system to behave very similarly. Here I've done it at 7 days, I could do it at 1 day, I could do it at 3 days, but I can say I need to get a certain total heat, which is a certain amount of reaction products. To do that, I'm going to take my cement plus my filler plus the heat that's associated with the seeds. I want this total heat because that's what I had from a pure system. I can take the amount of cement that I'm replacing. I can look at the amount of heat that's coming from the filler, the average heat that's coming from the seeds, and I can calculate out the volume replacement. Now, if I take out 32% of my clinker and I replace it with the seeds, and yes, the seeds do have their own global warming potential, but it's on par with cement and you use substantially lower amounts of it. I'm able to save about 70 kilograms of CO2 by doing this and having a very similar heat of hydration response, very similar early age strength development. The second example I'll talk about here is high volume fly ash mixtures. Now, these were set up to be similar to a bridge deck mix. So the original baseline case is a 0.42, right? And we're looking at trying to do this. The whole idea here is I can take advantage of that gel to space ratio concept, and I can reduce the water to cement ratio to get that certain strength at a particular early age. So if I do that, and I've got now a log scale plotted along the x-axis, the blue line is the conventional mixture that the DOT would be using. And if I simply start replacing fly ash in the system, right, and I change the water to cement ratio a little bit, what I'll notice here is all of a sudden just the fly ash replacement, I can start getting equivalent strengths at different ages. So I can get a similar strength by changing the water to cement ratio in that system because I'm changing the gel to space ratio. And when we first started doing this, people said, well, aren't you going to now start getting lots of early cracking problems or shrinkage problems because you're going to lower water to cement ratios? Well, here you can couple it with internal curing. And the coupling with internal curing has its own benefits because now you're actually curing the system properly, where low clinker systems are going to need attention paid to how we actually cure the systems. So here is our conventional system. Here's the system if we just drop the water to cement ratio. If we add the internal curing, we're back up here where we were with our initial system. If we look at the overall stress that develops towards shrinkage cracking, again, conventional system where we've just replaced the fly ash, where we've put in internal curing, we're getting no tensile stress developing in the overall system. The additional benefit that comes from this is now we can start to plot things like the electrical resistivity, right? And there's lots of people saying, well, this jump has to be because of more reaction. There's a huge nonlinear effect here because once you've filled the capillary porosity, it's much harder for the ions to start moving through the gel pores. So this big jump doesn't correlate necessarily with the amount of material that's reacting. It correlates with the fact that you've shifted the transport from the capillary pores, the big fat pores that everything wants to flow through, to the little tiny gel pores, and you now have a very long-lasting structure. So there's huge benefits in doing this. Substantial reduction in GWP, substantial reduction in the amount of clinker that's being used, but improvements in performance without problems with early age strength development. So in summary, reducing global warming potential is a real industrial need, and we will see more and more people pushing toward this, all right, in the coming years, and they need to do this soon. So there are many promising technologies out on the horizon, but there's things that we can be doing soon. Generally, we're replacing a lot of the cement clinker right now with SCMs. The SCMs can result in slower strength development. 3 ways that we can try to counteract that: quantifying the filler effect, using nucleating agents, nanomaterials, and altering our water to cement ratio to get to a similar gel to space ratio at your critical time. We showed 2 examples, one with the nanoseeds and one with high volume fly ashes, where this was demonstrated and shown that this could be done at scale and is actually being done in commercial plants.